So today I will talk about some ongoing work which relates to counting statistics in onset of Zeno effect. This work I am doing along with Professor Abhishek. And what I will present is only a part of what has been accomplished till now. So let me just begin by describing the system that we are looking at. It's a very simple two-state system in which the basic states are these, and we assume that the system evolves. This is the system Hamiltonian, which corresponds to a rotation about the x-axis. And at any given instance, the state of the system would in general be representable as a sum of these basis states. And we shall further assume that the system was initially. So what we'll do is that we will introduce the measurement of the system, and that we'll do by letting the system interact with another similar two-state system. And when the interaction will occur, the combined system will evolve in a Hilbert space, which will be a direct product of the Hilbert space of the system proper and the probe. So we shall initiate the probe in the system. Probe state will be chi0, which basically is just a notation for this state. Chi stands, that is the second product in any such summand would correspond to the detector or the probe, and the first product would correspond to the system proper. Now, during the time of the interaction, we assume that the system and the detector entangle and evolve in accordance with this equation. So the detectors Hamiltonian we assume to be almost trivial. Then the interaction process is such that the detector rotates about y, and this pi0 is a projection on chi0 state, and tau being the time interval between measurements, or we let the two entangle for the time interval tau. They evolve for time tau, and after time tau, the state of the combined system would be this. So this H is the Hamiltonian, and this. So if we do a proper expansion of this, then we obtain this combined state. So this is one measurement cycle, and at this instance, we make a measurement on the detector, and this measurement would reveal whether the detector is in the state chi0 or in the state chi1. This just evaluates to I chi1. And once we record the information that the detector has been observed to be in state chi0, then the unnormalized state of the system proper would be given by this equation. And if the detector is recorded to be in the state chi1, then the unnormalized state would be this. So these P0 and P1 are the probabilities of getting these readouts. So once these probabilities are known, and then once again we repeat the same measurement cycle, and then one can envision a sequence of probes continually sent to interact with the system. And on the other end, we keep recording the state of the outgoing probes. And therefore, we will have a record, a measurement record, which would be basically a sequence of 0, 0, 1, 0, 0, some stochastic evolution. Now, in the limit tau going to 0, we have shown in an earlier paper that the unnormalized state evolves according to this, as long as the readouts are always chi0. So we always read chi0. So if suppose as long as that happens, then the evolution happens in accordance with this equation, which can be solved using exponentiation of this matrix. And then we can define something called the survival probability, which is basically a measure of, or the probability of not getting a readout of 1 up till time t. So this, by definition, can be calculated once this equation has been solved. And this is fairly easy to do. And so I will note here these results for the survival probability that we obtain for various parameter regimes. This alpha, I should mention here, this is I alpha actually, sorry. It should be I alpha. So alpha here is basically so you see this is gamma, and gamma naught is the system's Hamiltonian frequency, and this gamma is the coupling frequency, and alpha is gamma upon gamma naught gamma upon 2 gamma naught. So one question that one has to address here is that why we are choosing this form of coupling. And the simple answer is that if you choose this form of coupling, then the Lindblad equation, the evolution will happen in accordance with Lindblad equation. So that's the principal reason for choosing this coupling. So our main parameter in this problem is alpha. And so once again, I will repeat, this is minus I alpha. So when alpha is less than 2, we get this expression for alpha. And so what we notice here, more importantly, is that the functional form of the survival probability undergoes a formal transition at the value of alpha equal to 2. And this can be seen as a phase transition, something that I will address also later. But so we should keep this in mind. And then this diagram is just this is just showing what is the survival probability after unit time against alpha. And another interesting feature of the value alpha equal to 2, where this switch between these two forms happens, is that if we calculate this limit, it goes to 0 as t tends to infinity. What this basically means is that for alpha is equal to 2, the survival probability decays at the fastest rate. And further, we could define something called the normalized state, which will be nothing but this, and then differentiate this equation and so on and so forth, and obtain an equation for the normalized state, which will be given by this equation. So it's a nonlinear equation. Notice that AT square is the component on chi0 of psi. So it's a nonlinear equation. And with the choice of the system Hamiltonian being proportional to sigma x.
Sorry, Varun, you have about 3 minutes left.
Oh. So with the choice of the system Hamiltonian being sigma x, we can show that if and the initial state is I chi is 1, then we can show that theta evolves in accordance with this equation. So what we model here is that as the probes keep coming, most of the times it would happen that we record 0, sometimes we record 1. So NT is the total number of jumps that are registered up to time t. And these follow the Ito differential equations, and d theta t, which basically comes from here. So this is the evolution under no click. That is, we are not getting any readout of 1. So this is the evolution under no click. But when a click happens, then the system jumps to the state to this state as we see here. It jumps to state psi 0. So so the value of theta goes to 0 at that instance. So this equation for theta was via this stochastic dynamics. But the important thing is that the stochastic dynamics is driven by this counting process with a stochastic intensity. But in theory, it is well known that this stochastic process with this stochastic intensity is a martingale of 0 mean. And using this fact, we can obtain a Fokker-Planck, generalized Fokker-Planck equation. And this has been also obtained via consideration of probability flow in segments of theta by Kumar and others. And their principal observation is for these values of alpha, we observe some transitions. We have already noticed that alpha is equal to 2 corresponds to transition point. But for a counting process, we can show that these are the principal statistics. That is the probability of no click up till time t, and these are the probability densities of clicks at instance t1, t2 till tn. So these are densities in time. And just like a Poisson counting process, no click or no count happens with probability e power minus lambda t in time t. For a stochastic intensity, this will happen with this probability, and this can be integrated to obtain this. And for various values of alpha, that is between, we can integrate this equation to obtain omega theta and this ratio. And we recover all the same probabilities that I have just now shown for various values of alpha. So this P0T0 indicates the probability of obtaining no count in time 0 to t.
So you have a minute left.
Yeah. So the other probability densities are these. So say, for example, probability density of obtaining single count at instance t1 between 0 and t would be no count from 0 to t1. Then the density of obtaining a single count in t1 to t1 plus delta t, and then no count in t1 plus delta t to t. So I'll not try to describe the whole calculation. So these are the formal expressions for P1, P0 at t1, one single click. Similarly, we can obtain expressions for t1, more than one clicks, and so on and so forth. So once we have that, then we can define the probability of exacting exactly n clicks in 0 to t interval, which will be given by this. And then this is a standard definition of the moment generating function and the expected value of the mean count. So once again, I will not go into the any details of the calculations, but I will just note here that the expected value of the mean count comes out to be these. And we once again notice that for alpha is equal to 4, there are transition points. As we see, we have already noticed there is a transition at alpha is equal to 2. We are noticing a transition at alpha is equal to 4. But there was another transition at 4 by root 3, which seems to be getting missed here. But in these expressions, in this first expression, if we expand this function in terms of the observers, then we notice that this factor, the first term will vanish for alpha is equal to 4 by root 3. So it's not clear at this moment whether this particular feature can be regarded as a transition based on just this information. But there may be some evidence of this in higher order statistics that we are still trying to figure out. And it would also be, should be also possible to obtain the complete solution of the generalized Fokker-Planck equation from the consideration of these probability densities that we have obtained. And so that is
yeah. So
thank you.
so